Swayam Prabha. Digital India. Educated India.
Welcome back for today's lecture on material and energy balances. So, we have looked at energy balances and we covered all the fundamentals, we looked at the basics and performed a lot of example problems. In the last few lectures, we have been summarizing all the concepts that we have learnt through energy balance calculations. So, today we will be solving a problem which actually tries to summarize all the concepts that we have learnt from both material and energy balances. In this problem, we would actually be performing material balances first in an extensive way for this multi-unit process, and then we will actually move on to working on the energy balance aspects, which will again cover most of the fundamental concepts that we have learnt throughout this course. So, this problem nicely summarizes all the aspects which have been covered over the past few weeks in this course. So, let us now go to the problem. So, the problem statement says a proposed method of producing methanol is to react CO2 with hydrogen. CO2, 1 mole of CO2 reacts with 3 moles of hydrogen to form 1 mole of methanol and 1 mole of water. Assume that the gross feed enters the reactor in the stoichiometric quantities needed for the reaction. Also, 0.5% nitrogen flows in with the fresh feed. On one pass through the reactor, 57% conversion is obtained. The concentration of nitrogen in the gross feed into the reactor cannot exceed 2%. How much heat must be added or removed from the system given here? Assume 1 kilomole of carbon dioxide enters the reactor every hour. So, here is the flow chart. So, you have a fresh feed which is coming in at 25 degrees Celsius containing carbon dioxide, hydrogen and nitrogen. It is getting mixed with a recycle feed which again contains carbon dioxide, nitrogen and hydrogen. However, this recycled gas is at 90 degrees Celsius, and here you end up having a gross feed which would contain carbon dioxide and nitrogen and hydrogen. Here what you have been given is it is 3 moles of hydrogen per mole of carbon dioxide, which is the stoichiometric ratio with which it is coming in. It has been told that the gross feed enters the reactor in the stoichiometric quantities needed for the reaction, and based on the reaction equation we know that for every mole of carbon dioxide there are 3 moles of hydrogen required. So, that would be the ratio which has been given here, and this gross feed enters the reactor where 57% conversion for a single pass is obtained. So, the gross feed, if you were to take reactor as the system, then you would have 57% conversion. So, if you remember the lectures which we had on systems with recycle and reactions, we would have discussed what single pass and overall conversion is. Here we have actually talked about, we have been given the single pass conversion. So, this means the feed which is passing through the reactor a single time gets a 57% conversion, and this results in the formation of product gases, and as you can see the product gas then goes into a separator where methanol vapor at 70 degrees Celsius, water liquid at 70 degrees Celsius are taken out as products, and you have a stream of gases which are the non-condensable components, namely carbon dioxide, hydrogen and nitrogen, which are actually leaving the separator. So, this is split into 2 streams, one is purged and the other is recycled. The purged stream is at 100 degrees Celsius and the recycled gas is at 90 degrees Celsius. So, this is the system which we are looking at. The 90 degrees Celsius is recycle is basically mixed with the fresh feed. So, now we have this process given to us. We have been asked to identify how much heat must be added to or removed from this entire system. Let us look at this process and try to perform all the required calculations. So, as I always say, the first step for performing any energy balance calculation is to perform material balances. Here we have been given 1 kilomole of CO2 enters the reactor every hour. So, which means the basis we have to use would be 1 kilomoles of CO2 in the gross feed. So, with that we would be able to perform the required material balance calculations. So, the first part would be to perform the extensive material balances that are required for getting the flow rates for all the streams. Once we have that, we can actually perform the energy balances. Let us go to the problem, let us try to solve this problem. Based on the information given to us in the problem, we can use the basis as 1 kilomole of CO2 in gross feed. So, we have been told that 1 kilomole of CO2 enters into the reactor, which means this is the gross feed and you have 1 kilomole of CO2 entering here. So, this is the basis given. So, we have also been told that the feed which is entering the reactor contains stoichiometric ratio of CO2 and hydrogen, and we have all, which is 3:1. So, which has also been given to us. So, now that we have that information, it would mean that the gross feed actually would contain 3 kilomoles of hydrogen as well. So, you have 1 kilomole of carbon dioxide and 3 kilomoles of hydrogen. So, in addition to carbon dioxide and hydrogen, you also have nitrogen. We need to find out how much nitrogen is accompanying this carbon dioxide and hydrogen. How would we do that? We have been told that the concentration of nitrogen in the gross feed cannot exceed 2%. So, which means we will use 2% as the concentration of nitrogen in the gross feed, and using that concentration, assuming that it is at the maximum threshold given, we will be able to identify how much nitrogen is present. So, if we were to assume nitrogen concentration, the nitrogen mole percentage is 2%. So, mole percent of nitrogen is equal to 2%. This implies what you have would be number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of hydrogen plus number of moles of carbon dioxide times 100 is equal to 2%. So, what you would have from here is, the only value we do not know is N2, which is the number of moles of nitrogen. The other values are already known. We know that hydrogen is 3 kilomoles and carbon dioxide is coming in at 1 kilomole, and the concentration, the mole percentage is 2%. So, the mole fraction is 0.02. So, using this we can actually calculate the value for the number of moles of nitrogen, and the value we would get would be 0.0816 kilomoles. So, we have 0.0816 kilomoles of nitrogen coming in. So, we also have been given that the single pass conversion is 0.57 or 57%. How would we be able to use the single pass conversion? How would we be able to use the single pass conversion? For using this value, we need to ensure that the reactant which is entering the reactor only passes through the reactor a single time. So, which means we have to take the reactor, the gross feed, as the component which is crossing the system boundary, and we need to ensure that the whatever is leaving does not come back through the recycle stream, and the system needs to be chosen appropriately. So, for this reason we could either choose just the reactor or the reactor and the separator. If we were to choose just the reactor, we do not have much information about the gross product. However, if we were to choose the reactor along with the separator, then we have a lot of information about the streams which are leaving the separator. So, for this reason we will choose the system of interest as reactor plus separator. So, the system we are using would be reactor plus separator. So, now that we have used the system, we can use the single pass conversion. The single pass conversion is equal to 0.57, right. So, this means we have 1 kilomole of CO2 entering. So, if 1 kilomole of CO2 is entering, how much is actually getting consumed? This implies 57% of this is getting consumed because of the single pass conversion. So, which means 0.57 kilomoles of CO2 is consumed. So, now to get information about CO2 which is leaving the system, we would have to write a CO2 balance. So, the CO2 balance for the system would be input minus output plus generation minus consumption equals accumulation. At steady state there will not be any accumulation, and as CO2 is a reactant, it is only getting consumed, there is no generation of CO2. So, you would have input minus output minus consumption equals 0, implying that output equals input minus consumption. So, we know that the input is 1 kilomole and consumption is 0.57 kilomoles, giving the output for CO2 as 0.43 kilomoles. So, this CO2 is actually leaving only through the stream P, because you have other streams here which are P2, P3 and P4. P4 does not cross the system boundary here, only the streams which are crossing the system boundary are P2, P3 and P. So, out of this P2 has only methanol, P3 has only water, P has carbon dioxide, hydrogen and nitrogen. So, the number of moles of carbon dioxide in the stream P is 0.43 kilomoles. We now have to calculate the number of moles of hydrogen in the stream P. So, using the same system, we need to now write a hydrogen balance. The hydrogen balance again is input minus output plus generation minus consumption equals accumulation. At steady state there is no accumulation, again hydrogen is a reactant, so there is no generation of hydrogen. So, your output again would become input minus consumption. So, input we already know is 3 kilomoles. So, what is consumption? So, consumption of hydrogen would also be equal to 0.57 times 3, because this is 57% conversion for a single pass applies for both carbon dioxide and hydrogen, because they are fed at stoichiometric ratios. So, this means the number of moles of hydrogen consumed would be 1.71 kilomoles. So, substituting this value for consumption and the value for input, we can calculate the output for hydrogen from the system would be 3 minus 1.71, which is 1.29 kilomoles. So, now we know that the product stream P contains 1.29 kilomoles of hydrogen and 0.43 kilomoles of carbon dioxide. We now need to identify how much nitrogen is actually leaving the system. Nitrogen does not take part in the reaction. So, the nitrogen balance, which initially would be input minus output plus generation minus consumption equals accumulation, can be simplified as input equals output, because at steady state accumulation goes to 0, and as it is not taking part in the reaction, generation and consumption would also be equal to 0, giving us nitrogen output as the same as input, which would be 0.0816 kilomoles. So, now that we have the information about the product stream, we can actually identify the mole fraction of all of these components in the product stream. So, why is this important? If we have the mole fraction of these product streams, we can actually identify the composition of the recycle stream and the purge stream, which can then be used for further calculations. Okay, so, we will try to find the composition of the stream P. So, composition of P would be, it contains carbon dioxide, which is 0.43 divided by 0.43 plus 1.29 plus 0.0816, giving a mole fraction of 0.239, and we have hydrogen, which is 1.29 divided by 0.43 plus 1.29 plus 0.0816, giving a value of 0.716, and for nitrogen the composition would be 0.0816 divided by 0.43 plus 1.29 plus 0.0816, giving a value of 0.0453. So, now we have the composition for the stream P, which in turn gives us the composition for recycle and the purge stream. As it is a splitter, we know that the composition would not have changed. So, we also need to identify how much of methanol and water are leaving the system which we had chosen. The system we had been working on is this, which is the reactor plus separator. So, to identify the amount of methanol, we have to write an methanol balance. So, methanol balance would be input minus output plus generation minus consumption equals accumulation. At steady state, accumulation goes to 0 and methanol is not being consumed as it is a product. You do not have any input of methanol, you only have output and generation of methanol, which means output for methanol, which is P2, would be equal to generation of methanol. So, looking at the stoichiometry, generation of methanol would be equal to the consumption of carbon dioxide. So, generation of methanol is equal to consumption of carbon dioxide. This implies P2 is actually equal to 0.57 kilomoles. Similarly, we can perform material balance for water. So, for the water, you would have input minus output plus generation minus consumption equals accumulation, getting simplified to output equals generation. So, this is the same logic as we used for methanol. So, generation, again looking at stoichiometry, generation of water is equal to is equal to consumption of CO2. This implies generation of water is equal to 0.57 kilomoles. So, therefore, output, which is P3, is equal to 0.57 kilomoles. Now, to get the information on the fresh feed and the recycle feed, we need to choose a different system. So, here we could use the mixing point as the system. So, if we were to use mixing point as the system, then we can actually write two different balances. One would be for nitrogen and the other could be for the total balance, and using these we will be able to solve for the two unknowns. The first unknown is the recycle amount R, and the other is the feed rate F. So, let us try to get this. So, let us first write the nitrogen balance. The nitrogen balance would be simple. You would have 0.0453 R. So, we had already calculated the mole fraction for nitrogen in R, which is equal to the mole fraction of nitrogen in P, right. So, using that we get this equation, which is 0.0453 times R, amount of nitrogen entering into the mixing point through the recycle, plus 0.005 F. So, we have been told that the nitrogen in the fresh feed is 0.5%. So, that means the amount of nitrogen entering through the fresh feed would be 0.005 F, and this is equal to 0.0816, which is the total number of kilomoles of nitrogen in the gross feed. So, we can also write a total balance. The total balance would be R plus F equals 1 plus 3 plus 0.0816. So, this would then become 4.0816. So, now we have two equations and two unknowns. So, solving these two equations simultaneously, we would be able to get the values for R and F. So, let us see what the values would be. Solving these, we get R equals 1.518 kilomoles and F equals 2.563 kilomoles. So, this gives us the values for R and F. However, we still do not have the information on how much carbon dioxide, hydrogen and nitrogen are actually entering through the fresh feed. So, how would we get that? So, that we can get by writing individual component balances for the mixing point. Let us now write the carbon dioxide balance for the mixing point. It would be input minus output plus generation minus consumption equals accumulation. So, no accumulation at steady state, no generation or consumption, it is a non-reactive system. So, input equals output. So, your input actually has two terms, one is through the fresh feed, other is through the recycle feed. We already calculated the value for the recycle feed, the molar flow rate for the recycle feed as 1.518 kilomoles. So, now we also have the composition of the recycle feed. So, we will have these two things separated. You would have one which is NFCO2, which is the carbon dioxide entering through fresh feed, plus 0.239 times 1.518, which is the number of moles of carbon dioxide entering through the recycle stream equals the total number of moles of carbon dioxide in the gross feed, which is 1. So, this means the fresh feed would contain 0.637 kilomoles of carbon dioxide. Similarly, we can write a balance for hydrogen. The hydrogen balance would basically be again input equals output. For a non-reactive system at with steady state, it would be input equals output, and the equation would be N hydrogen F plus 0.716 times 1.518 equals 3. So, solving this, you would get the number of moles of hydrogen coming through the fresh feed as 1.913 kilomoles. Similarly, we can write a balance for nitrogen, which would be again input equals output. So, you have nitrogen from fresh feed plus 0.0453 times 1.518, which is the number of moles of amount of nitrogen entering through the recycle stream. This would be equal to 0.0816. So, solving this equation, we would get number of moles of nitrogen entering from the fresh feed would be equal to 0.0128 kilomoles. So, with this, we now have the information about the fresh feed. So, we also need to have the information about the purge stream if we want to perform energy balance calculations for the overall system. So, for doing that, we will have to write a balance for the splitter, because we now have the information about the fresh feed, we have information about the recycle stream, we have information about P2, P3, we just need to get the information about P4. For this, we can write the total balance equation for the splitter. The total balance for the splitter would just be input equals output, and input is actually P, this is equal to R plus P4. So, solving for this, we would actually get P4 equals 0.2836 kilomoles. So, we knew the value for R, we had also calculated the value for P earlier. So, using these two values, we can calculate the value for P4. We already know the composition of the purge stream. The composition of the purge stream would be the same as the composition of the stream P and the recycle stream. Using that, we can calculate the number of moles of the amount of carbon dioxide, hydrogen and nitrogen in the purge stream. So, the purge stream basically contains 0.0678 kilomoles of CO2, 0.2031 kilomoles of hydrogen and 0.0128 kilomoles of nitrogen. So, this gives us the information about the purge stream as well. So, now we have all the information. So, we have the information about fresh feed, we have the information about the product stream for methanol, product stream for water, and the purge stream which contains all the carbon dioxide, hydrogen and nitrogen. So, we have information about the overall system, all the flow rates for the overall systems are available. So, the amounts now that are available can be used for performing the energy balance calculations. So, what is the energy balance we can perform? So, for performing energy balance calculations for the overall system, we need to first identify appropriate reference states. So, here in this problem, if you look at the problem statement, we have been given the reaction. So, this is the problem statement, right. So, the problem statement says that carbon dioxide reacts with hydrogen to form methanol and water. We have not been given the heat of reaction. So, we could either choose to calculate the heat of reaction using Hess's law explicitly and then apply this heat of reaction while we perform the calculations for energy balances, or we could use the heat of formation method where the heat of reaction is implicitly calculated while performing the calculations building the enthalpy table itself. So, here I have chosen to use the heat of formation method. So, for heat of formation method, we have to choose appropriate reference states. So, the reference states I have chosen are determined because of the method I am using. So, I am using the heat of formation method. So, for the heat of formation method, the reference states have to be elements as they appear in nature at 25 degrees Celsius and 1 atmosphere. So, this means the reference states can be carbon solid plus hydrogen gas, sorry not plus, hydrogen gas and oxygen gas and nitrogen gas, all at 25 degrees Celsius and 1 atmosphere. So, now that we have taken this as the reference state, we would have to build the enthalpy table. So, let us build the enthalpy table for the overall system. So, the overall system encompasses the mixing point, reactor and the separator. So, the only streams which are crossing the system boundary are the fresh feed which contains carbon dioxide, hydrogen and nitrogen, and you have the product streams which are methanol and water, and the purge stream which contains carbon dioxide, hydrogen and nitrogen. So, let us now write the enthalpy table for this. You would have carbon dioxide, hydrogen, nitrogen, methanol and water. So, these are the components which are crossing the system boundary. So, you have N in dot, H cap in, N out dot and H cap out. So, let us fill out the values. So, based on the material balance calculations we have performed, we know that 0.637 kilomoles of carbon dioxide enters through the fresh feed, 1.913 kilomoles of hydrogen enters through the fresh feed, and 0.0128 kilomoles of nitrogen enters to the fresh feed. There is no methanol or water entering to the fresh feed. So, let us look at the exit streams. We now have carbon dioxide leaving through the purge stream. We have calculated the number of moles of carbon dioxide leaving through the purge stream as 0.0678 kilomoles, and the amount of hydrogen leaving through the purge stream is 0.2031 kilomoles. Amount of nitrogen leaving through the purge stream is 0.0128 kilomoles, and you have methanol which is leaving the system as 0.57 kilomoles through the product stream P2, and water is leaving 0.57 kilomoles of water is leaving through P3. And now we have all this information. We had used the reference states as carbon solid, hydrogen gas, oxygen gas, nitrogen gas, all at 25 degrees Celsius and 1 atmosphere, right. So, for the heat of formation method. So, here the first component is carbon dioxide. Carbon dioxide coming in at 25 degrees Celsius, you would have some enthalpy associated with it compared to the reference state, because you have the formation of carbon dioxide. The next one is hydrogen, which is coming in at 25 degrees Celsius and 1 atmosphere. It is the same as the reference state, so this would be 0. Now, nitrogen coming in at 25 degrees Celsius and 1 atmosphere is at reference state, so which will also be 0. So, the exit streams, all of them are at a different temperature or exiting as a compound rather than the element, which means we would have to calculate all these enthalpies. So, this would be H2 cap, H3 cap, H4 cap, H5 cap and H6 cap. So, now we have to calculate 6 different enthalpy, specific enthalpy values. Let us first calculate H1 cap. The H1 cap is basically the first enthalpy where carbon and oxygen, carbon solid and oxygen gas at 25 degrees Celsius forms carbon dioxide at 25 degrees Celsius and 1 atmosphere. So, the reference state is carbon solid, and so the reference state used is carbon solid and oxygen gas at 25 degrees Celsius and 1 atmosphere. From here it goes to carbon dioxide at 25 degrees Celsius and 1 atmosphere. So, this which is the fresh feed for carbon dioxide. So, here only formation of standard heat of formation for carbon dioxide has to be accounted for. So, H1 cap would be equal to the standard heat of formation for carbon dioxide gas. So, this value can be obtained from any table. So, this value is actually minus 393.5 kilojoules per mole. Now, we have to look at H2 cap. So, H2 cap is again for carbon dioxide. However, the exit stream carbon dioxide is leaving at 100 degrees Celsius. So, we now have a process where carbon solid and oxygen gas at 25 degrees Celsius forms carbon dioxide at 100 degrees Celsius. So, the first step would be formation of carbon dioxide at 25 degrees Celsius, and from here you have the heating of carbon dioxide to form carbon dioxide at 100 degrees Celsius. So, the first step would have the heat of formation, and the second step would be a delta T term. So, your H2 cap would be equal to the standard heat of formation for carbon dioxide gas plus integral 25 to 100 Cp of CO2 gas dt. So, using the Cp of CO2 gas from any table and the heat of formation, we will be able to calculate this value as minus 390.6 kilojoules per mole. So, since CO2 is a combustion gas, instead of performing integral Cp dt, we would also be able to get the value for the enthalpy of carbon dioxide with reference to 25 degrees Celsius from a table, which is the combustion gas table which we had discussed earlier. So, we now have H2 cap. Let us look at H3 cap. H3 cap is nothing but hydrogen gas at 100 degrees Celsius. So, this is only the heating of hydrogen gas from 25 degrees Celsius, which is the reference state, to 100 degrees Celsius, which is the exit purge condition. So, this value can be obtained from the table, which would be 2.16 kilojoules per mole, and H4 cap can also be obtained from this kind of a table. So, H4 cap is for the nitrogen at 100 degrees Celsius. So, again from combustion gas table you will be able to get this value, which is 2.19 kilojoules per mole, and we now have to look at H5 cap and H6 cap. So, what is H5 cap? So, H5 cap is for the change in enthalpy for the process where carbon solid, hydrogen gas and oxygen gas forms methane. So, these are all at 25 degrees Celsius, the reference state is at 25 degrees Celsius, and it forms methanol gas at 70 degrees Celsius. Now, we need to perform calculations to get this. So, the first step would be formation of methanol gas at 25 degrees Celsius, and then would be heating. So, initial step you would be looking at the standard heat of formation for methanol gas, and the second step is delta T. So, your H5 cap is actually equal to standard heat of formation of methanol gas plus integral 25 to 100 Cp of methanol dt. You have to use the Cp of methanol gas and you will be able to perform this integration. So, the value here would be minus 201.2 plus integral 25 to 70. So, this is at 70, I am sorry, not 100. So, 70 would be 0.04293 plus 8.301 times 10 power minus 5 t minus 1.87 times 10 power minus 8 t squared minus 8.03 times 10 power minus 12 t cube dt. So, the value for Cp I obtained from the tables. So, from here I can calculate H5 cap as minus 199.09 kilojoules per mole. So, similarly we have to calculate the value for H6 cap as well. So, for H6 cap you have hydrogen gas and oxygen gas at 25 degrees Celsius forming water liquid at 70 degrees Celsius. So, the first step is formation of water liquid at 25 degrees Celsius, and from here it is heated. So, the first step is just heat of formation, standard heat of formation for water liquid, and the second step is delta T, which will be integral Cp dt. So, your H6 cap would be equal to the standard heat of formation for water liquid plus integral Cp of water liquid dt, and the temperature is from 25 to 70. So, using the value for Cp for water, you would be able to get this value for H6 cap as minus 282.45 kilojoules per mole. So, the Cp for water would be 0.0754 kilojoules per mole degree Celsius. So, using that we have been able to calculate H6 cap. Now that we have calculated all the enthalpy values, let us go ahead and fill the enthalpy table. So, the enthalpy table which we had was CO2, hydrogen, nitrogen, methanol and water. So, we had N in dot, H cap in, N out dot and H cap out. So, the values for N in and N out are 0.637 kilomoles, 1.913 kilomoles and 0.0128 kilomoles. So, please note that these values are all in kilomoles and the values for H cap we calculated were all in kilojoules per mole. So, make sure you convert it appropriately while you perform the final calculations, and these are all in kilojoules per mole. Okay. So, this value we have calculated as minus 393.500 and here we have these values as 0.0678, 0.2031, 0.0128, 0.57 and 0.57. So, this values for enthalpy are minus 390.6, 2.16, 2.19, minus 199.09 and minus 282.45. So, now that we have all the enthalpies, we can calculate delta H. So, delta H for this process would be, we can calculate the total enthalpy of the outlet stream and subtract the total enthalpy of the inlet stream from that value. So, this would give us minus 49,834.3 kilojoules. So, if we were to look at the general energy balance equation we would have used, so for the open system the energy balance equation would have been Q minus Ws equals delta H minus plus delta Ek plus delta Ep, and you have no change in kinetic potential energy, no moving parts. So, with this would give us Q equals delta H, and Q, which is the amount of heat supplied or removed from the system, would be minus 49,834.3 kilojoules. So, with this we have performed all the required calculations to get the amount of heat transferred. So, if you looked at this problem, here we actually had a multi-unit system with recycle and purge and a reaction. So, for this type of a system we actually performed all the required material balances to get the information about the fresh feed, purge stream and the product streams, and once we had this information we went ahead to perform the energy balances for the overall system. For this overall system we have actually been able to calculate the amount of heat which needs to be transferred, and here we took the into consideration the heat of reaction in an implicit way by using the heat of formation method. So, this particular problem summarizes all the aspects which we have been looking at and gives us a succinct overview of all the fundamental concepts that have been covered through this course till this point. In the next lectures we will now start looking at systems which are not in steady state. Until this point all the systems which we have been working with have been systems at steady state. So, in the next lecture, from the next lecture onwards we will actually look at systems which are not in steady state, and we will look to see how material and energy balance calculations can be performed for such unsteady state processes. Until then, thank you and goodbye.